Hello and welcome to this physics video, and in this video we're looking at the first part of electromagnetic effects. Look at what a specification may say. Well, it's quite a lot there, but basically what we're going to try and do in this video is cover what's called electromagnetic force, electromagnetic induction, difference between AC and DC, rotating coil generators, the transmission of electricity, and the use of transformers. So there's a lot to get through, and some of it you may be thinking, God, I don't understand that at all. Well, I just recommend at this point you take it slowly. If need be, pause the video, go back, make notes, whatever. Take your time and don't get overawed by it, okay? Let's make a start. Now, a lot of the stuff on this, as I said, is a little bit overwhelming. So look at the first bit here. Show understanding the conductor moving across a magnetic field or a changing magnetic field linking with a conductor can induce an EMF in the conductor. Now, as my friend the dog here is, like most of us, saying, what? What's an EMF? Well, EMF is an abbreviation of what we call electromotive force. Now, when charge flows through a cell, and by this we're talking about a battery cell, it's given energy by the cell. It's the whole point, isn't it? The whole point of a battery cell, it gives it energy. So the number of joules of energy given to each coulomb of charge that passes through the cell is what we call the EMF, or electromotive force of the cell. Now you may be thinking to yourself, sounds a lot like voltage. Well, in fact, you're absolutely right, because what is energy given to charge? We call it voltage. So EMF and voltage, same principle. Now, let's think about this over here, a moving conductor through a field. Now, what do we need to have? A few components, let's look at them. So we need to have a conductor. Any piece of wire will do, as long as it's a conductor. We need a magnetic field. So here we've got North Pole and South Pole, so we've got a magnetic field. Something else we need is movement. Now, the movement of the wire in the magnetic field. If we get that, we will actually find we get a small EMF or voltage being generated. It's all the amazing things about physics, isn't it? This is. Let's look at this. Well, the production of EMF is moving a wire in a magnetic field, and this is known as what's called electromagnetic induction. So make a note of that. Okay, it's a really important point over here. Electromagnetic induction. And what it does, it involves a wire being moved in a magnetic field. Now, here we've got a magnetic field, north, south. Here are the magnetic field lines here. Here we've got a wire. The wire is connected to a very, very sensitive meter called a galvanometer, and this will measure the voltage or EMF going through the wire. So moving the wire downwards through the magnetic field induces an EMF. So as long as there's movement of the wire, we will get a reading on the meter as shown here. Now, if we move the wire in the other direction, i.e. up, we get an EMF in the opposite direction. So our meter will show an opposite deflection. Okay, so we've got movement, and also we've got a magnetic field producing a current. Now, the induced EMF and therefore the current can be increased by, first of all, if you move the wire faster in the field, you get a bigger EMF. If you use a stronger magnet, so these lines here are stronger, you get bigger EMF. Increasing the length of wire in the field, now you can't keep increasing this on automatic, can you? But if you loop it into some sort of coil, okay, that will have the desired effect. Now, this is first developed by this guy here called Michael Faraday, and Michael Faraday came up with Faraday's law of electromagnetic induction, and he stated this: the EMF, which you now know what it stands for, induced in a conductor by the wire, is proportional to the rate at which the magnetic field lines are cut by the conductor. So the quicker you cut the field lines by the conductor, the bigger the EMF that is produced. Wow. Now, how can you put that into practice? Well, what we need, several things really. Well, there's two options. Basically, there's two options, isn't there? We can move the wire in the magnetic field, like we've got here. So we can move the wire. One thing is to move the wire. Now, can you think of the second thing? Well, the second actually is keep the wire still and move the magnet. So you can either move the wire in the field or move the magnet. Two options. Now, for this one, you can make the wire into a coil. So there's our coil there of wire, and as long as the magnet is moving, you're going to get a current. So the bar magnet is pushed into the coil, i.e. this way here, and the EMF is induced in the coil.
If the magnet is withdrawn from the coil, i.e. this way, you'll get an EMF in the opposite direction. So going in, you get it going one direction, going out, you get it going the other direction. So long as there is movement of the magnet, you will get an EMF. Now the induced EMF and current in that, which is follows on, can be increased by first of all moving the magnet faster. So the quicker you move this in and out, the bigger the EMF, the stronger the magnet, or the more turns you have on the coil. Isn't that clever? So you can generate electricity in this way. That is just amazing. Now talking about electricity, we talk about electricity in two ways. We have what's called AC and DC. So we understand hopefully now we understand what's meant by an induced EMF. But let's think now the difference between AC and DC, as it says over here in the specification. Now your battery cell is a source of DC. So DC stands for direct current. The current flows only one direction. Batteries and solar cells supply DC electricity. Now you may have at your school, wherever you work, what's called a cathode ray oscilloscope. Now you can connect up the cathode ray oscilloscope to the battery, and that will show you the voltage being produced. Now before you connect the cell to the oscilloscope, the trace on the oscilloscope will be along this line here. As soon as you connect the cell to the oscilloscope, the trace will be deflected. So it deflects according to what voltage is being supplied. So if, for example, each one of these divisions represents, let's say, a volt, we've got 1 volt, 2 volt, 2.5 volts. So we can see there that 2.5 volts is being supplied by the cell. So if connected to a cathode ray oscilloscope, the trace on the screen is a straight line deflected from the zero. If you change the terminals round on the battery, the deflection would be down here instead. Okay? Now, AC is what we call alternating current, and in this one the current is constantly changing direction. It's not going in one direction, it goes in back and forth very rapidly. Now mains electricity is AC, and in the UK every plug you've got in your house works at about 230 volts, and that's got a frequency of 50 Hz. That means it changes direction 50 times every second. Remember, Hertz is a unit for frequency, so 50 Hz, it means that the current is changing direction, so positive, negative, 50 times every second. Right, so that's the difference there between DC and AC. Now we're going to come on to some really challenging stuff now, and you've got to go through this really slowly and follow it, because it is supplementary, i.e. for extension papers. The specification asks to describe and explain a rotating coil generator and the use of slip rings. Now let's go back to Wikipedia. Can't beat good old Wikipedia, can we? We can, but pretty good as anything. In electricity generation, a generator, now generators are also known as alternators. A generator is a device that converts mechanical kinetic energy, that means movement energy, into electrical energy for use in an electrical circuit, external circuit. Okay, so to build a generator, Bob the Builder says we need two things. We need, first of all, a magnetic field, and we need a moving wire. Hopefully now, on the previous work on EMF, you now understand that these two things are necessary to produce current. So here we have basic setup. Okay, first of all, we've got magnetic field. Now these magnetic poles here are producing magnetic field going from north to south. So here we've got what's called magnetic flux going between the two poles of the magnet. Secondly, we've got a coil. Now remember we said that a coil is better than a single wire, it produces a stronger EMF. Now the coil is made of insulated copper wire. Now the thing is, what happens is you rotate this in the magnetic field. This is rotated, the coil here is going to rotate. You do that by turning the shaft of the coil, and you do that use a little handle if you want to, attach a handle here and turn it, and that'll give you enough movement there to generate EMF. You also need to have a slip ring. Now slip rings are attached to the coil. We'll see this in a moment. There's a coil there. The slip rings are attached to the coil. As the coil rotates, the slip rings rotate as well. And the last thing we need are brushes. Now brushes, normally made of carbon, they rub against the slip ring. Let's look at that in detail. Okay,
So here's your coil, okay. Here's your slip rings. Now these are fixed to the coil, so these spin with the coil. The brushes are in contact with the slip rings, okay. So brushes keep the coil connected to the outside part of the circuit. So as the EMF is generated in the coil by movement in the magnetic field, that current is then taken away by these brushes. As the coil rotates, it cuts magnetic field lines, so an EMF is generated, and as I said, a current flows. The beauty of the slip rings is they keep the coil in contact with brushes at all times throughout the rotation, and as a result the current flows in alternate directions, producing alternating current, AC. I think we need a bit more explanation there, don't you? Now this represents the north and south, and here's our coil here, and this is the trace on our oscilloscope. So when the coil is in the vertical position here, no current is being generated because the coil isn't breaking the field. Now when the coil is in this direction, you've got maximum forward current because you've got maximum breaking of the magnetic field, okay. So your oscilloscope will show us maximum current in the forward direction. We continue to rotate the coil, okay, and here again it goes to 0. Now when it gets to here, okay, the coil has got maximum effect, but this time in the reverse direction, because can you see this is flipped over to there. It's now the opposite side, so we've got maximum reverse current, and back here is 0 again. Now we can increase the maximum EMF, okay, by increasing number of turns on the coil, increasing the area of the coil, making it a bigger coil, using a stronger magnet. We can rotate the coil faster, can't we? Yeah, we can, all those things. Okay, so hopefully now we follow what's meant by the term EMF, and also how we can use a rotating coil to generate a current. Now let's go on and look at the transmission of electricity. Having made this electricity in a power station using a rotating magnetic coil, how do you get it out to the homes? Well, power station is connected to transmission lines, and these are connected eventually to home. You may see these if you walk out in the country. You may see these massive pylons carrying wires. Those are all part of the, what we call in a minute, the national grid. Now our previous diagram, that one there, is a bit oversimplified. Let's look at more detail, shall we? Now a power station produces electricity at a whopping 33,000 volts. Now sounds a lot, but it's not good enough for transmission. We need to increase that, and for that we use what's called a transformer, and specifically we use what's called a step-up transformer to whap up the voltage to an incredible 400,000 volts. So those lines you see going across the country, what are called national grid of transmission lines here, they are carrying electricity at a whacking 400,000 volts. That is a lot. Now for use in the industry and home, we need to step it down a bit, so we have what's called a step-down transformer. A step-down transformer decreases the voltage, a step-up increases it. So here we've got a step-down, what are called a substation, and this may decrease it to, I don't know, 132,000, a little bit less. That will then be transmitted, and then go to a further substation where it will be stepped down to perhaps 33,000 volts for big industrial areas perhaps. Now when we go in towards towns, we'll have further substations, and in towns you may have light industrial areas, small factory units, and there they may want 11,000, so it's stepped down for them at 11,000. Now 11,000 is far too much for use in homes and shops and so on, so we'll also have substations near our homes. You probably see one of these if you walk not far from your home. You'll probably see a transformer substation. They're normally green, behind fences to keep you out, but in there you're stepping down the voltage, so it's being stepped down from 11,000 to 230 for use in farms, use in schools, homes, shops, offices. So you can see there how we transmit electricity. Now this is what's called the national grid. So the network of pylons and cables that carry electricity across the country is known as the national grid. Now why do we have such a high voltage? Well, power is transmitted through the cables here, high voltage. That means we can have the current low. So high voltage results in current being reduced. If the current is reduced, there's less heat being lost, and also means we can use thinner lighter and cheaper cables. So we're saving energy and saving money by stepping the voltage up to 400,000 for transmission. It then has to be subsequently stepped down using transformers. Okay, let's look at transformers now and think how they work. Now, transformers, as I said, are used to increase or decrease voltages. This is really important. Get this please clear. Transformers only work with AC. They will not work with DC. So make sure you've got a note of that. Here's a transformer. Now, transformer starts first of all with a soft iron core. So there's our transformer core there. It's soft iron. Now we'll have what's called a primary input coil. This one here is the primary input coil. We can see here, if you count, there are 5 turns, and this is denoted N1. So 5 turns here, N1 is 5. We have an input voltage called the primary voltage, V1, and in this case it's 12 volts. We've got 12 volts going through this coil. We'll also have what's called a secondary output coil, and you can see here that this coil, if you count them up, has got 10 turns, so N2 is 10. Now, as a result of this, the output voltage is higher, 24 volts, and the output voltage or secondary voltage is V2. Now, this is an example of what we call a step-up transformer. Why? Because we're increasing the voltage from 12 volts to 24 volts. How have we done that? We've done it by increasing the turns from 5 to 10. We double the turns, we double the voltage. Clever stuff, huh? Now, in a step-down transformer, the voltage would be decreased. So understand, please, the difference between step-up and step-down transformers. Now, why does it happen? Well, it looks like magic, doesn't it really? I still think, I think it's an amazing process. It's all to do with what's called an induction. So when AC flows through the primary coil, it sets up an alternating magnetic field, okay, induces an alternating magnetic field in the soft iron core, and so therefore that alternating magnetic field is picked up by the secondary coil here. Now, this changing field induces a voltage in the secondary coil, and hence you get a current flowing. Now, this is a big proviso. Provided all field lines pass through both coils, okay, that's magnetic field lines, pass through both coils, and there is no heat loss. Big if there, because there's going to be heat loss. The following equation applies. So the equation applies in an ideal situation. The output voltage, i.e. the secondary voltage, divided by the input voltage or primary voltage is equal to turns on output coil or secondary coil divided by turns on input coil. Or we could say V2 divided by V1 equals N2 divided by M1. And that is the equation we need for transformers. And what I've done here, I've just rearranged them all for you. So if you don't know what N2 is, you use this equation, or V1 and so on. Okay, I've just made it easier for you there by rearranging the equation, but you should be able to do that yourselves. So there's the equation again. Let's look, here's an example. A transformer has 20 turns in the primary coil. So N2 is 20. 10 turns in the secondary coil, so M1 is 10. Input voltage is 50, so V1 is 50. What's the output voltage? Now, what we're looking for here, looking for the output voltage V2. So we're going to use this equation here. Let's see what happens. So we know V1 is 50, N1 is 20, N2 is 10. How do you know that? Because I told it in the question. Duh. So V2 is 10 for N2, 50 for V1, 20 for N1. So work it out, it comes 25 volts. So V2 is 25 volts. So voltage has been reduced from 50 volts to 25. So we can say this is a step down transformer. And that's all you have to do in these calculations. Now, I'm saying all you've got to do, well, here's some examples here. So here we've got the primary voltage, secondary voltage, number of turns in N1, and all you've got to do is to calculate number of turns in secondary and work out if it's step up or step down. So think back, number of turns in secondary, N2. So for this one you need that equation there, don't you? Okay, so can I suggest now you pause the video and have a go at answering these. I'll give you the answers in a moment. So don't cheat, pause the video now, have a go. Okay, I'm assuming you paused it, had a go. Here's the answers. So first case 200, that's a step up. Second one it's 10, that's a step down.
Next one's 2000, step up, and the third one 1500, a step up. Okay, hope you got those right. Pretty straightforward. And that is the end of this video. So that's everything we've covered. We've covered a huge amount today, so I hope that you go back and have a look at this video again, make any notes. Don't use this as your only resource. Make sure you use your exercise books, textbooks, brain, and else you've got to use. Take it all on board. But I just want to thank you now for listening to me. Thanks for watching the video, and I'll be back with you with the Electromagnetic Effects Part 2 very soon. So bye bye for now.